Hello. So today we have chapter 9 about 10 event, survivor analysis, and sensory data. So is survivor is the most frequent term, but the more general one is time event. So you want to apply this technique outside of biology or medicine. So that's the term that you should try to find. So when we talk about survival analysis or time event, these models, in this model, the outcome variable is the time until the event occurs of any other numeric variable that have been censored of any limitation during the data collection. In consequence, times are always positive, and we need to use distribution like Weibull distribution. So when we have our target variable, we have always the minimum of 2 events or 2 times. Or we have the event time, the feature, the survivor time also is named when the event happens or take place, and when the time is censored. For example, when you are studying the chart, you have a limited time to know if a customer will churn or no. So you just know if before the study ends, the customer churns, so you will have a T event, or you don't know maybe, or the study end before you can confirm if churn or not, or the passing time. So basically, a part of the target variable, J, we also have this indicator that we use delta to indicate it. So we use 1 when the event happen, take place, and 0 when not. As a result, when delta equals 1, we observe the true survival time, and when delta equals 0, we observe the sensory time. In the next example, we just could observe the event for 2, this should be 2 of 3 patients, and before ending the study. So in this example that we can find in the book, for patient 2 and 4, we didn't know what happened. We don't have the event time, but we'll have it for number 1 and number 3. So some use cases is when you need to know the time for individual to find a job again. So it's like, oh, you lost your job. How many days or months do you need to find a new job? The time needed for a letter to be delivered. You are, for example, working in logistics. The time needed for a cab to pick you up to your house after having called the house company like Uber. So you go to the application and you, hey, lead me to that place. Also, this model can help you to analyze that kind of data. The time needed for a customer to churn. Oh, when a measured instrument cannot report values above certain number. So, for example, you are measuring distance and you have a limitation, so you cannot measure more than certain amount. So you can also use this kind of models. Do you have any doubt related to this definition or any comment? Okay. So when we are making this analysis, we need to take in consideration some assumptions. So we need to validate that the time, the event time, T, is independent to the sensor time. So what that means, the point is like, if you don't observe this time, you shouldn't expect that the person died the next day. So they have the example patients who drop out of the cancer study early because they were very sick. So if they were very sick and they drop out the study, they might die some days after. So in this case, yes, the event time and the censoring time are correlated. As soon as somebody, so it's important to check why the time was censored to understand the reason. That's the main explanation they have in the book. If we don't check that, we overestimate the true average of survival time. So we are expecting that this person would live a little bit longer. We don't know how much, but longer. Know that they would die the next day. So in that case, we overestimate the survival time. The other one is predictors are independent to sensory event. Yeah, this is something that we can check using the data, checking that our predictors are not correlated with that variable. For example, in our study, very sick males are more likely to drop out the study than very sick females. That would drive a wrong conclusion that men survive longer than females for this indicator. So yeah, we need to be sure that this one is also independent. In this book, we are going just to check the right censoring. That is the most popular one. But there are also cases of less sensory or interval sensory that we could find in another books how we can deal with that. I don't have any idea on when is really necessary to use this kind of model. I don't know if it's just the way that you shape or you define the problem that shape this kind of relationship. So I don't know if you really need to learn or we just need to shape our model, our problem in the right censoring type. So when let's about how we're going to measure this. We have the Kaplan-Meier survival curve. It measures basically the probability that we have a population have to have the event after a certain time. So for example, like what's the probability you get cancer when you are 50 years old? You know that this probability should be higher than you have just 5 years old. So it's always increasing. So the survival curve function is defining a probability that event T happens later than time T. As a result, the larger value of S, the less likely the event would take place before time T. So yeah, as higher is this value, so you probably won't get that before. So you expect that after. And they have this example using the brain cancer data. So we have 88 observations and we have 8 columns. So we have the time and the status, that is our delta. And also another variables to explore. Here we make just a simple count and we say, okay, we are checking if the time is greater than 20 or no. So it's the first check. And also we want to check if we see the censoring or the event time. So if we try to estimate the probability, so to estimate this amount, the probability of that event happen after 20 years, we could think that we could use the total, the 30 plus 12, 88 observation that the event so didn't happen. So the event time is greater and divide by the total, but that will overestimate our probability. As we don't really know, as we cannot assume that these 17 really ended life at that moment. Another solution could be don't use that 17. So instead of using 88 in the denominator, we could use just subtract that amount. But it also would have we will underestimate our probability. So that's not the real solution. So these both author Kaplan and Meier use conditional probabilities to make to calculate that probability. And in the resources of the book, I found this video, and the author really explained really well how is the approach, because before we check the theoretical way, so the mathematical situation.
So I'm just going to show the Kaplan-Meier estimate in pictures. That the details are in the textbook. But here's an example. So I've got 5 patients here, okay, and so the patient number 1 died at time y1. So how the Kaplan-Meier estimate proceeds, it kind of unfolds in time. One goes to the first failure time, the first death, and 4 of the 5 patients survive past y1. So the probability of surviving past y1 is estimated to be 4/5. Okay? Then we move on to the next failure time. Notice we skip this censoring time because it's not important for this calculation, although it's going to come in here. Well, there's 3 patients remaining, 1, 2, 3. 2 of the 3 survive past y3, so the probability of surviving past y3 is 2/3. So overall, the probability of surviving past y3 is 4/5 from the first times 2/3 from the second event. So what this method does is it computes the conditional probability of surviving past each failure time, given you've survived up to that time. So there's a series of conditional probabilities, and we just multiply them together, right? Because to survive past here, you have to survive past here. That's the first hurdle, and then you have to survive the next hurdle at y3. And finally, y5 is the last failure. No one of the only one person made it is at risk here, and 0 made it past. So the probability of surviving past y5 is 0. So the overall probability ends up down at 0.
So a very clever way of taking into account the censoring and using as much of the censoring information as you can, because they go into the denominators of these probabilities.
Right. So this guy, he didn't get his own estimate, but he participated in the risks in the calculation here. He dropped out here, so he didn't participate here. So the censored observations participate as long as they're in the study, basically, which seems perfectly reasonable.
It's a very simple idea, but in retrospect, fantastic. And often the best ideas are simple.
And here's the resulting Kaplan-Meier curve.
So that's the process that we are going to explain now in the mathematical way. So we start defining each unique event time. So in the example of the video, they have 3 event times. 1, 2, and 3. So we pick the time value for each one. Then we count the number of patients who died at each of the time. It's like we are creating a table. And we count the number of patients that were alive in the study before the lead time and at-risk patients. And we see that the probability of the event happened after ascertain the number would be also the probability that happened before. So okay, so it's like this value, the event time, should be greater than this current G, supposing that the same T is greater also than the previous unique value. So if we are putting in the same order, so the lower goes first, then the greater goes after in decreasing order. No, increasing, it's increasing order. So that's the base formula. And based on the total probability, we see that probability, but we know that the second term would be 0. But is it possible to patient to survive time D if he or she did not survive until earlier time? So we don't need the second term. So at the end, you will need to start for the last value onto the first one. And we make a product. And this is a state-wise function, as we always keep. So if there is no any new die in the data, the probability keep constant until someone dies. That's basically as we have a state-wise function. So if the survival curve can help us to answer some important questions. So we can answer with this curve, what is the probability that breast cancer patient survive after 5 years? So we just need to use the probability of the S at 5. Or we also can have answer question with the complement. Out of the 10 employed people, how many do you expect to have a job again after 2 months? So in this case, we need to use the complement of the probability. But it also works in the other sense by selecting the quantile in the y-axis and checking the value on the x-axis. So what is the typical waiting time for a CAP? So you go straightforward to 50% of survival probability and check the related value in time. So you can check what is in the using the quantiles. If you go, if you see the graph in the other way around, it also works in that way. So to perform this survival curve in R, we use the survival package and we use the subfield and define the formula in this way using the sub function, defining the time and the status and the data. And we also can get the data using the sub-meaner, sub-summary. So if you want to see the whole table, you can use that function, or you can just use Bloom tidy and you will have the same table. So maybe the sub and the estimate is maybe the difference between it's the same column, but they call it different. And for the sub-meaner, also you have a really good options to plot the survival curve using ggplot. And we have some options like adding this table below, and the breaks that we want to use, select also the median survival value, and also the color of the curve. I prefer blue. And have some options that you can check the documentation. If you use surf without placing the status of the delta, it will assume that all the events are, so all the times are even times. If you don't specify that, and you can compare both charts using this combined function, in placing all together in a list. So as we can see, the correct one, the probability to survive is greater then they were wrong because they were assuming that the censoring time was all as a event times. So yeah, the gap is really big. We also can use, we can also assume a probability distribution for the events. We usually use the wayboard, but we also can use some difference. So to make that with the survival package, we first start creating this vector of probability of not probability, like possible probabilities, like values in this range. So from 0 to 1 at this step. So we use the subgraph function, and we use and we place the formula in the same way as before. And then we need to use this function to predict. And we need to use 1 minus the survival probability as maybe here, I don't know, you have the function. Is it like the survival function is the hazard, and we are estimating this function, and the derivative of the hazard is the -1, so something like that. So it's the inverse that we are using this time. We create data frames with this variable, and this package is really specific about the cons that he expects the information. So the time need to be in the time column. The survival probabilities should be also in the sub column, so there is no any option here to change that. And we can plot here the survival curve based on the Weibull distribution. Now maybe here I don't have, but inside of the subgraph there is an argument of this, and maybe of this. So the default is Weibull, but you can select between all this kind of distribution. If you say names to this variable, you will see even more distribution to select from. And okay, once we really understand the distribution of the survival time, how in general is the function, and we want to compare groups. We want to know if female survive more than male. If we see this chart, it seems that yes, that females tends to survive more than men, but is that statistically significant? So to solve that question, we can use the log run test. It has many names, as you can see here. And basically, instead of just calculating one risk group, we need to divide the risk and the number of people. And I think that the people have died. We can see here the definitions. And number of people that have died, yeah. And here is the die time. So we need to divide between both groups. We use this statistic. They define each value and place all together. And the point is that these W have a standard normal distribution, and they use the normal distribution to find out the p-value related. In this case, the study have a 0.2 p-value that's really high, and there is no evidence that this difference between female and male is statistically significant. So we cannot reject the null hypothesis. That's really interesting because the book starts with this this test, and it's not significant, but when they use the cost bus model to check the same relationship, the results changes. There is more information. Do you have any question right now or something that you want to comment?
No questions right now, but I really appreciate how you walk us through this.
Okay, great. Yeah, so the point is like even before, to me was interesting, and maybe the main point about this is that when we have data collected for, and we don't really are making a close experiment, it's much better. We use several predictors to check the relationship, because as this wasn't a close study, just observe data. It's not like you select and place a random experiment. So maybe for this reason, the result wasn't so important in this test. So in my opinion, it was like, okay, if I'm not running an experiment by myself, I don't use this. Maybe that's the conclusion I take from that explanation that is in the book. So to explain the regression models with the survival response, we first need to understand the hazard function. The hazard function, rate, or force of mortality is the useful estimate the risk of an event and measures the instantaneous rate. So conditional probability under unit of time at which events occurs, given that the event has not yet occurred in the subject of the study. So it's like a derivative, because you have this delta t with the limit to 0. So as you can see here, we are getting the probability that t happens just after this t time happened, that it hasn't happened. So based that the event hasn't taken place yet. And it's important to notice that this is not a probability, it's correlated with the probability, but it's not probability, but it can be greater than 1. That's the point. That's the only reason that it's not probability, because it can be greater than 1, but it's really correlated with a probability. So as higher is this number, you have the higher probability to die. That's the point. So the t is the time on observed survival time. So on observed in the case that you haven't seen it, and t is the extremely tiny number, and is that measure has a close relationship with the probability density function of t. That is the one that we were discussing, that we use Weibull to get it. So this is the definition. The only point that we don't have the conditional probability that doesn't happen. That's the only difference between the hazard and the probability function. So they make a little bit of math, and they end with this relationship when the hazard is the function probability on the survivor function. But also, if we derive the survivor function, we also get a negative. So the point is, like, if you have one of these three, you can get the other one around with simple calculations. I tried to simulate an example of the hazard. So at this point, as using this definition, if we assume, for example, that the probability density function of t is a normal distribution, so we just need to pick the density under the survival function. So the survival function would be this area in this side. So it's like, if at this point, I was calculating over some points, but I just keep it clear here. It's like, okay, at 6, the density probability is 0.24. And the probability to get the event after that time is 0.16. And the hazard rate would be 1.53. So as you can see, it doesn't matter, it always increase. At that time also increase. So to model the survival time, we could use the linear approach. That's basically to calculate the hazard based on our predictors using an exponential function with this intercept and this linear product. And we use the likelihood function to, we optimize it with the likelihood function, and based on the optimal value of this likelihood, we select the coefficients of this regression. The problem with this is that it won't be really, it's like too linear. That's the linear approach. They recommend a most flexible approach, that is the COTS model. So instead of assuming an intercept here, we assume a baseline hazard that can take every function shape, every distribution, and we also have the relative risk. So plotting both together, we have a prediction of the hazard. They explain that this is also as general that this function shaped into this one, as this intercept could be moved to be part of the baseline hazard. So the most important assumption to keep in mind, a 1 unit increase in S corresponds to an increase of the hazard by a factor of the coefficient. So basically, we expect that between one group, so it will have one variable that have just 1 and 0, a dummy variable. We expect that both pools always have the coefficient as a difference between both. Normally, we are taking the hazard, or we are just plotting the survival curve. Well, the model doesn't support is when we have one group that overlap other in the process. It's like this function is like our linear models, but without the capacity to add interactions. So yeah, the model don't see interactions. And what else? Okay, and as this function is too general, we cannot use the likelihood function. They need to use the partial likelihood. That is a really interesting way to cancel out that baseline hazard function. In the example of our brain cancer data, we can see a table of probabilities. Yeah, we can have a standard deviation, set a score, p-values, thanks to the long-run model test, as they create test statistics, so we can make inference based on that. And here we can see that a diagnosis of HG lymphoma has a higher probability to die, as it has a higher hazard. That basically. So the estimated hazard patient with this diagnosis is E over 2.15, so 8.58 times greater than patient with different diagnosis if we hold all other coverage fixed. In the higher, the King's Cup, so the key I, the lower the chance of dying at a given point of time, as the coefficient is negative. And yeah, and both are significant. The other ones are not significant based on this model. So we have like 5% on favor to believe. So the point is that we need to translate using the exponent function to get these values. And yeah, so we have this is the publication data. Maybe I didn't get the, let's see what approach. Okay. The publication data, and they see the difference between if the results are negative or positive. So if you have a study and the study was not significant, so they say it was a negative result. And that's basically, they want to understand if there is a different type of publication between both studies. And yeah, it seems to be, so they use a cost model to relate both cases. And just checking the graph, they say, yes, the model are different. The results are different. Negative result has a lower chance to be publicated. So if we want to run a cost model, we just need to use the cost pH function using the same structure as before. We have here the coefficients. Okay, to create that chart using R, we need to create a grid for the levels that we want to plot. So it just plot categories. So you have a numeric value as the key. You need to select certain value. So I just pick the median and the 75% percentile. Then you pass this output to the subfit function, bring the data, also the grid. And yeah, we don't need confidence intervals. Now that we have the model, we use summary to get the data. We pick as character. We create these little variables, and just we plot here. And we can see all the clues together. So we can see that if we compare for every diagnosis, if we have a higher P, KI, the chances to survive are greater in each color. And yeah, the glioma has more probability to die. We saw in the table before. If we want to use the wearable model to the same data, we use the subreg, and here we can see the coefficients. Even though I don't know, I didn't check if you have a summary table, but well, we can see that the glioma has a negative. So it's like the Weber function with the intercept, you need to interpret it in the opposite way. If in the Cosbot model, a positive for a number would think that you would die, in this case, use a distribution. If you have a negative, you will die faster. That's the point. So the coefficient have a different sign, but we can see the same relationship. This value is most higher, and this is positive. So yeah, we'll have really similar results. Just we'll follow the same process. We create a distribution probability. We create our grid. Okay, this grid function comes from data from point dot table. So don't worry, just the same span grid, just using data table syntax. And we pass to predict, and we make sure that all variables are aware, making some manipulations. We always need these variables, so as the function expect. Oh, I'm getting now. Let's go back. And yeah, we can see the same result. So the glioma is here, it's green. So yeah, higher values of the king have lower probability to die. And but in glioma here have the higher probability to die. Here's glioma. It's the same. Here's glioma here. So basically, I see the result really close to each other. So there are two different ways to see the same reality. So we also can apply skin range to the cost model. We just need to change our partial likelihood function to have also this tuning parameter. So the P, so we can apply a Hughes penalty or a lasso penalty. In the example, they apply the lasso penalty to see that the lower value happens at this point, and then it increases. So yeah, we can also apply this model when we have a lot of variables and we need to apply some feature selection. That is a really good news. So model evaluation. Model evaluation is it's tricky in this kind of model. So we cannot use our usual metrics for the model in time. To compare predicted and the true survival time, we need to figure out how to use censored observations. That's maybe the key point here. And to turn the survival curve into survival time. So, if you see here, the COTS model doesn't predict survival times. They predict hazard times. So, how do we know how well we are predicting, or we are predicting the risk? So what we need to do is first estimate the risk score. So multiply its coefficient to the predictors, and then classify our variables, our test data, into the risk level, and check if the categories don't overlap. That's great if you just have one model of possibility, but if you want to compare between many models, we need to use the C index. It's like the ROC, the R under the curve of the ROC curve. So the name is Harris Concordance Index. Harris is just one option. There are more options related. So we quantify the probability that greater risk scores, so the risk score that we define here, are attributed to subjects with higher chance to experiment the event. So what we need to know is if the risks that we are predicted It's really the real risk that we are seeing in the data. So basically, what we check is the probability that the risk for a certain number is higher than other if the survival time, if the event time of this event is lower than this one, and the event was censored at the time of the study, basically. This is the function. It's like an accuracy measure, but it's not exactly accuracy. To understand the function was a bit challenging, so I asked ChatGPT to make me an example and I will share with you. So if we have just one predict and we got a coefficient of 2.5 or whatever study we did before, we have also this test data. So we have our predicted S 1, 2, 3, 4, 5. That's our predicted value. And the survival time would be 3, 4, 5. So I just check here. The S is always increasing. The survival time is always increasing. And we have two sensory dates. So we start to calculate our weak score. So we just need to multiply S times the 2.5 and we get the numbers. And here is that when it was the most tricky part. We need to compare the IDs for the when Y is higher than Y. So as 2, so as 4 is higher than 3, we compare the subject 2 and 1. That's basically. So if we go to the 5 subject, we see that 7 is higher than 7 is higher than 6, than 5, than 4, than 3. And for that reason, when we go here to the table, we see that they are comparing 5 with 4, 5 with 3, 5 with 2, 5 with 1. Because that's the main rule. So that's the way that they select the measure to compare each other. So, and they start to compare if the risk of the 2 is higher than the risk of the 1. No, I think no, the risk of the 1, yes, is higher than the risk of the 2. And all is increasing. Yeah, it's always false. Then we multiply by the event and get the sum of both. So in this case, for this example, all was 0. But that's basically the number. And I was trying to find an example in R, but it's like this function is not implemented in a lot of ways. I think I saw a package. It's dry grab. This one. They have the C index, and it also have a cross-validated version. Yeah, cross-validation index. Yeah, and they ask us to place the formula, the data, and I think that's all that they need to apply and get this value. My only concern about this function is that they get the cross-validated, but it might not work for the test the test approach. So when we are making machine learning, we try first to split our data set, maybe 30% to the test data and all to the training data. And with the training data, we apply the cross-validation. But I haven't seen any function to apply the test approach test, our test C index. Well, I think that with the training would be enough, maybe. And okay, and that's it. That's what I have. You have any part that you want to review with me or wasn't clear? Yeah. So I think we already